In first lecture, I explained definition of sets. Then what we'll study in the chapter that we have explained. In our this second lecture, I will talk on the concepts, subsets, operation on sets, laws for operations on sets. So firstly, what is meant by subset? Let X be set and we have other set, say Y. Then Y is subset of X if each element of Y lies in X. That is, Y belongs to X for every Y belongs to Y. Y belongs to Y. Y belongs to X for every Y belongs to Y. Then we say that Y is subset of X. Notation: if Y is subset of X, then it is denoted by Y subset of X. So this is subset of X symbol. Now Y is subset of X. On subsets, we'll talk about now operations on sets concept. Operations on sets. So if A and B are two sets, then first operation is union. A union B is nothing but set of those elements X such that X belongs to A or X belongs to B. By using the Venn diagram, if I have some set A, I have some set B, then in union we have to take elements of A as well as elements from B. So this complete shaded portion denotes A union B. Second, intersection operation. So intersection contain common elements in A and B. So it is set of those elements which lies in A as well as in B. Notation: A intersection B, set of X such that X belongs to A and X belongs to B, or and. In by Venn diagram, if I have A set, B set, then this shaded portion denotes A intersection B. This whole shaded portion denotes A union B. Other operation is nothing but difference of sets. So third operation is difference. If A and B are two sets, then A minus B is set of those X belongs to A such that X doesn't lie in B. So by Venn diagram, what is the portion of A minus B? This is A set, this is B set. You have to collect all those elements only from A, but they are not members of B, means from A we have to remove the elements from A intersection B. So this set is nothing but this part. This is shaded portion is A minus B. Fourth one, symmetric difference operation. Difference asymmetric difference B is nothing but A minus B union B minus A. So it is set of those elements which lies in A or in B but not in both. So it is precisely A union B minus A intersection B. By Venn diagrammatically, if I have A set, this is B, this is your A minus B, this is B minus A. Their union is asymmetric difference B. Means A union B minus A intersection B gives us asymmetric difference B. Complement operation is there. Complement. If A subset of universal set, this is universal set, then A complement is denoted by A to the power C or A dash, and it is nothing but U minus A. It is set of those x belongs to U such that x doesn't belongs to A. Set up all those elements from U which are not members of A. That set is called as complement of A. Here we have talked about union operation, intersection, difference, symmetric difference and complement operation. While talking about union, intersection, difference, symmetric difference operation, we have taken two subsets or two sets, and on that we are applying that union, intersection, difference or symmetric difference operation. Means to talk about those operations we require two members. That's why these operations, union, intersection, difference, symmetric difference operations are binary operations on collection of sets. While complement of set, to talk about a complement of set, we are just taking just single subset of universal set, and by using that universal set and that given set A, we can compute a complement. So to talk about the complement, if given set is related to its complement, means that operation relating given set to its complement, that become unary operation. Unary means one. Instead of real number, if I talk about the negative of given real number with respect to addition operation, for A minus A is the negative element, A is related to its negative element, then that operation is unary operation. But if I have to take addition, multiplication operation, then I have to take two real numbers. So that operations are binary operations. Okay, so while defining that operation, if you require two elements, then that operation is known as binary, and while thinking about operation which is defined only by using single element, then it is known as unary operation. This is difference between binary and unary. Complement operation is unary operation. Now if I observe Venn diagrammatically, if I take A union B, it is same as B union B, that one. Means union operation is commutative operation on collection of sets or family of sets. A intersection B is same as B intersection A. So intersection is also commutative operation. A minus B is not commutative. A minus B is not same as B minus A. A minus B is this shaded portion, while B minus A will be this part here. And therefore, difference operation is not commutative. What about the symmetric difference operation? A symmetric difference B is same as A minus B union B minus A. So, symmetric difference operation is also commutative operation. Other laws about these operations, union intersection operations, are associative operation on collection of sets. We know that addition, multiplication are commutative associative operation on set of numbers. Means if I have three different numbers A, B, C's, then if I have to take addition of that three numbers A, B, C, then if one will take addition of A and B first and then he will add C there, while other student will take addition of B and C and then he will add A in that. Means A plus B plus C is equal to A plus B together first plus C. So if I interchange position of bracket, so by taking addition in any way, A plus B plus C, so first student will add B in A and then C in resulting addition, other B plus C first and then he will add A there. On same line for union, if I have three different sets A, B, C, then if I have to take union of that three sets, A union B union C, if one take A union B and then he will insert the elements of C in that union and other will take B union C first and then he will insert elements of A in B union C, both answers should be same, equality is there, means union operation is associative. Same law hold for intersection operation also. Intersection operation is also associative operation. So these operations are commutative associative. Now distributive laws, we know that addition, multiplication operation distributes or addition in set of number means A into B plus C is equal to AB plus AC. On same line, union operation distributes over intersection and intersection also distributes over union operation. That is, so what are the distributive laws? For three sets ABC in universal set, A union B intersection C is same as A union B intersection A union C. And A intersection B union C is equal to A intersection B union A intersection C. Means union distributes over intersection, intersection distributes over union. These are distributive laws. De Morgan's laws. So just by using Venn diagrams you can verify these laws, these equality hold there. De Morgan's laws for A comma B subsets of say universal set U, first A union B its complement. So complement of union is equal to intersection of their complements. Means A union B whole complement is equal to A complement intersection B complement, and second A intersection B its complement is equal to A complement union B complement. Complement of intersection of two sets is equal to union of their complements. I can extend these laws for arbitrary union as well as arbitrary intersection. Means if A alphas are subsets of universal set, then union of A alpha, where alpha where is in index set, its complement is equal to intersection of A alpha complement, alpha where is in index set. This union may be finite, countable union, or union of arbitrary number of subsets. Similarly, intersection of A alpha, its complement is same as union of A alpha complement. These laws are extended. Okay, so these are De Morgan's laws. Now We are just revising concept of sets. Now our next aim is to talk about the functions. Which are studying from 11th standard. Function is a very important concept in mathematics. To talk about the function, firstly we must know Cartesian product of two sets, then relation, and then we will define function in terms of relation. So what is the relation? Firstly, Cartesian product of two sets. Cartesian product. If A and B are two sets, then A cross B is a set of elements of order pair or set of order pairs AB where A varies in A, B varies in B. Set of order pairs AB where first element is from A and second is from second set, then set of those order pairs is called as A cross B. By observation, if A has say m elements, B has n elements, then for every element in A, we will get n pairs. So total number of pairs in A cross B will become m into n. So if number of elements in A is m, number of elements in B is n, then number of elements in A cross B, Cartesian product of A and B, is m into n. In a subset, R of A cross B is a relation from A to B. From A to B. Means empty set is also one relation from A to B. Empty set is subset of every set. So whole A cross B is also subset of A cross B. Now if number of elements in A is K, number of elements in B is equal to S, then number of elements in A cross B is equal to K into S. Just I have explained. We know that if X contains K elements, then X has 2 raised to K subsets, or power set, which is nothing but collection of all subsets of X, contain 2 raised to K subsets. So therefore, number of elements in power set of A cross B is equal to 2 raised to Ks. 2 raised to Ks. This is nothing but number of relations from A to B. From A to B. Okay. It is difficult to take examples here because our main aim is to study countable and uncountable sets with help of function, and that's why I am not interested to explain the relation in detail. I require relation concept only for defining function. Okay. Now we'll take function. Let A and B be non-empty sets. Then relation F from A to B. Instead of R, I am using F is the first letter of function. Means F is subset of A cross B. F from A to B is function if it relate every element of A to unique element of B. To unique element of B. That type of relation is known as function. Now here, if I suppose A, B, C, 1, 2, 3, 4, if I take A is related to 1, B is related to 2, means here this relation are contain two pairs A1 and B2. So it is a relation from A to B, but that relation doesn't assign C to any member of B. So we are getting contradiction to every element of A. Therefore, this relation is not function. This relation is not function. Now, if I take other one, say R is equal to now A1, B2, B3. This is also subset of A cross B. It relates A to 1, A has only one image. It relates B to two different elements in B. But we require only one assignment for any element of A in B. But here there is one element in B having two images, and suppose C is also related to 4. Every element is related to some elements in B, no problem about that, but there is one element which is related to two different elements. That's why we are getting contradiction to this condition. Therefore, this relation is not function. So if I drop one arrow from here, then I will get A to 1, B to 2, C to 4. The three pairs. Means in function relation that F contain number of pairs is equal to number of elements in A set. Number of elements in A set. If that number of pairs are less than number of elements in A or greater than number of elements in A in case of finite set A, then it is never function. Then it is never function. This is about function. Now, if f is a function, so if I take now this f as a1, b2, c4, as f relate every element of A to unique element in B, means A is related to or X is related to Y, this is written as or X related to Y by F. This is written as Fx is equal to Y or Y is equal to Fx. Y equal to Fx. So f of A is 1, f of B is 2, f of C is 4. But in previous example, what is f of B? I cannot write it uniquely. That's why I cannot write this in this form. So I can write function by expression now. Is it clear? Moreover, if f is a function from A to B, then we write f from A to B. This is the notation for function. For this function, A is called as domain of f, B is called as codomain of f, codomain set. Then what is the range? Range of f is equal to f of A. It is set of fx where x sphere is in A. So if I take that in order pairs, f of a is 1, f of b is 2, f of c is 4, means 1, 2, 4. That will be here 1, 2, 4. Set of images from codomain set is nothing but range set of f, which is denoted by f of a symbol or r of f, or you can just write range f. Range f. This is about function concept. Now, other types of function, one function. A function f is said to be 1 if any two distinct elements in A have distinct images. Means if you are able to find at least two elements having same image, then that function is not 1. Here this function is 1. This function is 1. But instead of this c, if I take f of c equal to 2, f of b equal to f of c equal to 2, but b is not equal to c in domain set, then this function is not 1. This function is not 1. If I take f from R to R as fx equal to x square, then f of 1 equal to f of minus 1 is equal to 1. F of a equal to f of minus a is equal to a square, where a is non-zero. So for two distinct elements I am getting the same image, then fx equal to x square is not 1 function. That is the concept of oneness. On to a function is said to be onto if every element in B has some preimage in A under that function f. Now here, for this function, 3 has no preimage. So there is no any element in A which is related to 3 by that f. Therefore this function is not onto. So function will become onto if range of f is whole codomain set B. Whole codomain set B, then in that case f is called as onto function or surjective function. One function is also known as injective function or injection. While a function f is said to be bijective function or one correspondence if it is 1 and onto both. If function is not 1, means you will get at least two distinct elements having same image. In that case, that function is called as many-one function. So 1 function is never many-one and many-one is never 1 function. While a function is said to be into function if range of f is proper subset of codomain set B. Range of f is not equal to B, then that function f is called as into function. So if f is not onto, then that function is into function. So into function is not onto function is not into. Bijective function concept is important to talk about the equivalent sets. What is meant by equivalent sets? Two sets A and B are said to be equivalent sets if there exists some bijective function f from A to B. Then we say that A and B are equivalent sets. We require this equivalent sets concept to talk about countable set, uncountable sets, etc. So with this discussion, today we will stop here. In next lecture, we will take some results depending on function, and then we will apply equivalent set concept